Tonight, we're exploring what happens beneath the surface of our seemingly solid planet. Right now, you're sitting on ground that feels perfectly stable and reliable. That sense of security represents one of nature's greatest magic tricks. What if the solid foundation under your home is actually floating on a restless planetary engine? What if those rare, terrifying earthquake moments reveal something extraordinary about how our planet actually works? We'll discover why certain places shake violently while others remain mysteriously calm. You'll see how underground rocks behave more like slow-motion rubber bands than the permanent stones we imagine. We'll trace invisible networks of geological stress connecting distant regions across thousands of miles. And we'll explore how these underground dramas reveal Earth's interior. It is far more dynamic than the quiet, stable world we experience day to day. So settle in. Before we begin, leave a quick note in the comments, where you're listening from, or one thought you're carrying tonight. I read them, and they genuinely help shape future journeys. If you'd like more nights like this, subscribe, only if you enjoy these late-night journeys. Now let's begin. Ancient civilizations had a simple explanation for earthquakes. Gods were angry, monsters stirred underground, evil spirits shook the earth in rage. These supernatural theories persisted for thousands of years. The alternative seemed impossible. Solid rock couldn't possibly bend and break like fragile materials. This comforting belief would prove spectacularly wrong. Geologists made their breakthrough in the early 1900s. They discovered something that fundamentally changed our understanding of planet Earth. Underground rocks don't behave like the rigid stones we see on the surface. Deep beneath our feet, even the hardest granite gets pushed and pulled by immense forces. These forces can move entire mountain ranges. Underground rocks act remarkably like steel beams in a skyscraper. They stretch, bend, and store enormous amounts of stress before reaching their breaking point. Picture a massive rubber band being slowly stretched over many years. The material stores energy as it deforms. It still looks relatively normal until you push it just 1 millimeter too far. Then it snaps back with explosive violence. Underground rock formations work exactly the same way. These geological rubber bands are kilometers thick. The snapping process releases energy equivalent to thousands of nuclear weapons. Here's what makes this process so extraordinary. The underground stress builds gradually over human lifetimes. The 1906 San Francisco earthquake resulted from tension accumulating since 1857. 49 years of slow, invisible underground stretching. All of it suddenly released in 60 seconds of catastrophic ground motion. Rock that seemed solid and permanent had been secretly preparing for violent failure. Most people think earthquakes are rare, dramatic events that occasionally make headlines. This creates one of the most misleading impressions about our planet's actual behavior. Earth doesn't experience earthquakes occasionally. It experiences them constantly. Our planet operates more like a constantly humming machine than the quiet, stable world we imagine. Earth generates over 1 million earthquakes every single year. That's roughly one earthquake every 30 seconds. Somewhere on the planet, 24 hours a day, 7 days a week. Complete seismic silence would actually indicate something has gone catastrophically wrong. We live on a world that never stops talking to itself underground. Only about 100 of those million annual earthquakes are strong enough for people to actually feel. The remaining 999,900 constitute a continuous background murmur. This happens entirely below human detection. Most of these tiny tremors last only milliseconds. They release energy equivalent to a small firecracker exploding deep underground. The scale range is absolutely staggering. At the quiet end, micro-earthquakes barely register on sensitive instruments. At the catastrophic end, great earthquakes release energy that is roughly 32 billion times more powerful. When these monster earthquakes occur, sensitive instruments detect the resulting vibrations anywhere on Earth's surface. The entire planet rings like a giant bell for weeks afterward. This persistent seismic activity follows geographic patterns. These patterns reveal our planet's hidden architecture. About 90% of all earthquakes cluster along narrow bands. These bands mark boundaries between Earth's major crustal plates. They include underwater mountain ranges where new oceanic crust forms. They include deep ocean trenches where old seafloor plunges back underground. The infamous Pacific Ring of Fire alone accounts for roughly 3/4 of the world's earthquake energy release. Imagine a cosmic savings account that accumulates enormous deposits for decades. Then it withdraws everything in a single, catastrophic transaction. That's exactly how earthquake energy works. We experience earthquakes as sudden, terrifying events lasting less than 2 minutes. But the power behind them represents the largest energy storage system operating on our planet. Underground rocks function as geological batteries that charge slowly and discharge explosively. The numbers reveal energy scales that challenge human comprehension. A magnitude 9.0 earthquake releases energy equivalent to 32 billion tons of TNT. That's roughly 2 million times more powerful than the atomic bomb dropped on Hiroshima. This enormous energy doesn't appear from nowhere. It accumulates gradually over 50 to 200 years. Massive crustal plates push against each other with pressures exceeding 100 million tons per square mile. Underground rocks absorb this stress like springs being compressed in extreme slow motion. Here's what makes this energy accumulation process so remarkable. The same geological forces that build mountain ranges over millions of years also load underground stress systems. These systems eventually trigger earthquakes. Plate tectonics operates like a planetary engine. Heat from Earth's interior drives continent-sized slabs of rock across the surface. Where these plates collide, separate, or grind past each other, enormous stress concentrates along fault zones. Sometimes these zones span hundreds of miles. During the stress accumulation phase, underground rocks undergo continuous deformation. This remains completely invisible at the surface. GPS measurements reveal that opposite sides of major fault systems move past each other at rates of 1 to 4 inches per year. That seems incredibly slow, but across 50 years, the accumulated displacement reaches 20 feet. Underground rocks stretch to accommodate this motion until they reach their elastic limit. Then they snap back to their original shape with devastating violence. Regions with no history of seismic activity suddenly started experiencing regular tremors. The timing and location of these new earthquakes pointed to a shocking conclusion. Humans had learned to trigger earthquakes accidentally. The breakthrough discovery came from monitoring earthquakes near large construction projects. Underground mining operations triggered thousands of small tremors as excavated chambers collapsed. Even large-scale water reservoir projects created earthquake swarms. Enormous weight from artificial lakes stressed underlying rock formations in ways they'd never experienced. But the most dramatic example emerged from hydraulic fracturing operations. Injection wells used to dispose of wastewater from oil and gas extraction began triggering earthquake sequences. Areas like Oklahoma historically experienced almost no seismic activity. Between 2009 and 2015, Oklahoma's earthquake rate increased by 2,500%. The state went from recording 2 earthquakes per year to over 900 annually. Here's what makes human-induced earthquakes so fascinating from a scientific perspective. They operate through exactly the same underground stress mechanisms that trigger natural earthquakes, just on faster timescales. Injecting millions of gallons of pressurized fluids underground changes stress conditions along existing fault systems. The added fluid pressure acts like geological lubricant. It allows rocks that had been locked together to suddenly slip. What would normally require decades of natural stress accumulation happens in months or years. These artificially triggered earthquakes rarely exceed magnitude 5.0, but they still cause significant damage in regions where buildings aren't designed to withstand seismic forces. More importantly, they reveal that earthquake systems operate much closer to their failure thresholds than anyone previously realized. Human activities that seem minor on geological scales can push underground stress systems past their breaking points. They send messages racing through the solid earth at speeds that would impress any telecommunications engineer. These seismic waves travel so efficiently that a magnitude 9.0 earthquake in Japan can be detected by sensitive instruments in Antarctica. Just minutes later, our planet operates like a giant musical instrument that vibrates as a unified structure when struck forcefully enough. Earthquake waves come in distinctly different varieties. They behave like separate underground messengers carrying different types of information. The fastest waves, called primary or P waves, compress and stretch rock as they travel through Earth's interior. Speeds reach up to 8 miles per second. These represent the earthquake's first announcement. They race ahead to warn seismic stations that more violent shaking is approaching. They arrive like advanced scouts reporting that the main army is coming. Secondary or S waves follow behind at slower speeds, but pack much more destructive power. These waves shake rock from side to side with motion that can topple buildings. S waves travel at roughly 3 miles per second through solid rock. But here's their most remarkable characteristic. They cannot pass through liquid materials. This property allowed seismologists to discover that Earth's outer core consists of molten metal. S waves from earthquakes on one side of the planet never appear at detection stations on the opposite side. Surface waves represent earthquake motion's most devastating messengers. These waves roll along Earth's outer layers like ocean swells moving across the seafloor. Surface waves travel slower than both P and S waves, but they carry enormous amounts of energy and can circle the entire globe multiple times before finally dissipating. During great earthquakes, surface waves create ground motion so violent they permanently alter the landscape. They form new lakes. They change river courses. They trigger massive landslides hundreds of miles from the original rupture zone. Thin outer skin protects increasingly dense rings toward the center. Earth operates on exactly the same architectural principle. Our planetary onion spans about 4,000 miles from surface to core. It contains layers so distinct they behave like completely different worlds stacked inside each other. Each layer follows different physical rules. Each operates at different temperatures. Each plays unique roles in the geological drama happening beneath our feet. The outermost skin we call the crust represents Earth's thinnest layer. Under continents, this rocky shell reaches maximum thickness of 45 miles. Under oceans, it thins to just 3 miles deep. That's like the skin of an apple scaled up to planetary dimensions. This seemingly substantial foundation supports all human civilization. It actually represents less than 1% of the distance to Earth's center. Beneath the crust lies the mantle. This massive layer of hot rock extends 1,800 miles toward Earth's center. This isn't the solid stone most people imagine. Mantle rock exists in a strange state between solid and liquid. It flows like extremely thick honey over millions of years. Temperatures reach 4,000 degrees Fahrenheit. That's hot enough to melt copper instantly. Pressures exceed 500,000 times atmospheric pressure. Under these extreme conditions, solid rock behaves like slow-motion lava. The outer core begins 1,800 miles underground. It extends another 1,400 miles toward the center. Here, iron and nickel exist as churning liquid metal at temperatures approaching 9,000 degrees Fahrenheit. This molten metal ocean generates Earth's magnetic field through constant circulation patterns. These patterns are powered by the planet's rotation and internal heat. Without this liquid metal dynamo, solar wind would strip away our atmosphere within a few million years. At Earth's very center sits the inner core. It is a solid sphere of iron and nickel. It is compressed under pressures 3.6 million times greater than atmospheric pressure. Despite temperatures exceeding 10,000 degrees Fahrenheit, hotter than the surface of the sun, this metal remains solid. Extreme pressure prevents it from melting. This cosmic ball bearing, roughly the size of the moon, spins slightly faster than the rest of the planet. We live on a world built like a perfectly engineered machine. The seemingly solid ground beneath our feet actually behaves like puzzle pieces on a cosmic game board. These massive puzzle pieces have been engaged in the world's slowest dance for billions of years. They reshape continents and ocean basins at speeds so gradual they're invisible to human perception. Each piece measures between 30 and 100 miles thick. They float on the hot, flowing rock underneath like rafts on a very slow river. The Pacific Plate, larger than the entire Pacific Ocean, slides northwest toward Asia at exactly 3 inches per year. That's roughly the rate your fingernails grow. This particular fingernail happens to be 64 million square miles in area. It carries the entire Pacific seafloor along for the ride. The North American plate drifts westward at 1 inch annually. It gradually separates from Europe and widens the Atlantic Ocean. These motions seem impossibly slow, but across geological time they add up to continental-scale migrations. The driving force comes from deep underground circulation patterns in the mantle. Hot rock rises from near Earth's core. It spreads horizontally beneath the crust. Then it cools and sinks back toward the depths in cycles lasting hundreds of millions of years. This creates a planetary conveyor belt system that never stops running. Plates get dragged along by these underground currents. The evidence for plate movement appears everywhere once you know what to look for. Identical fossil species appear on opposite sides of the Atlantic Ocean. This reveals that Africa and South America were once joined together. Mountain ranges line up perfectly when you mentally reassemble continents like puzzle pieces. Volcanic rock shows magnetic patterns that record ancient pole reversals. These create stripe patterns on the ocean floor that track seafloor spreading over millions of years. What seemed like permanent, unchanging geography actually represents a single snapshot. It captures an ongoing continental migration that's been reshaping Earth's surface for over 3 billion years. India spent 50 million years traveling north from near Antarctica to collide with Asia. This collision created the Himalayas, through slow-motion continental collision. Australia continues drifting northeast, gradually approaching the equator. We inhabit a dynamic planet where even the continents refuse to stay put. These boundary zones represent the planet's most geologically violent neighborhoods. Forces equivalent to millions of nuclear weapons constantly push, pull, and grind massive rock slabs against each other. Three distinct types of plate interactions create the major earthquake zones that ring our planet. Each generates characteristic patterns of seismic violence through different underground wrestling techniques. Transform boundaries operate like planetary grinding machines. Plates slide past each other horizontally. The San Andreas Fault in California exemplifies this geological violence. The Pacific Plate grinds northwest against the North American Plate at 2 inches per year. This might sound gentle, but the friction between continent-sized rock masses creates stress that accumulates for decades. Then it releases catastrophically. Divergent boundaries function like underground assembly lines. New oceanic crust forms as plates separate. The Mid-Atlantic Ridge represents Earth's longest mountain range. It stretches 10,000 miles underwater from Iceland to Antarctica. Here, molten rock wells up from deep underground to fill the gap. Europe and North America gradually separate. This seafloor spreading process occurs mostly beneath the ocean. It generates thousands of small earthquakes as fresh rock crystallizes. The seafloor literally tears apart at rates of 1 to 4 inches annually. Convergent boundaries host the planet's most spectacular geological violence. Oceanic plates plunge beneath continental plates in massive subduction zones. The ring of fire surrounding the Pacific Ocean marks these underwater collision zones. Cold, dense oceanic crust gets forced down into the hot mantle underneath lighter continental crust. As the descending plate reaches depths of 400 miles, it triggers the largest earthquakes on Earth. It also feeds volcanic chains that span entire continents. The mechanical details explain why certain regions experience devastating earthquakes while others remain seismically quiet. Most of North America's interior sits safely within a single tectonic plate. It's far from any boundaries where underground wrestling occurs. Meanwhile, places like Japan, Chile, and Indonesia experience constant seismic activity. They sit hectare on top of active subduction zones where oceanic plates continuously dive beneath continental margins. These geological combat zones generate 90% of the world's earthquake energy. Then they snap back to their original shape with explosive violence. This process, called elastic rebound, operates like a geological rubber band. It gets pulled tighter and tighter until it finally breaks free and whips back with devastating force. Understanding this underground spring mechanism revolutionized earthquake science. It revealed why seismic activity follows predictable patterns despite seeming random and chaotic. Picture holding both ends of a thick rubber band and gradually pulling them apart. Initially, the rubber stretches smoothly and stores energy as elastic tension. The material deforms but maintains its structural integrity. It accumulates stress that wants to snap the rubber back to its original length. Eventually, you reach the elastic limit. 1 more millimeter of stretching causes catastrophic failure. The rubber band breaks or slips from your grip, releasing all stored energy instantly and violently. Along major fault zones, tectonic forces gradually deform rock formations. They bend rocks on opposite sides of underground fractures. The 1906 San Andreas rupture occurred because the Pacific and North American plates had been grinding past each other for 49 years. They slowly bent and twisted rock formations up to 20 feet out of their normal positions, surveying measurements before the earthquake revealed fence lines, roads, and streams that had been gradually offset. Underground rocks accumulated enormous elastic strain. When rocks finally reach their failure threshold, the stored elastic energy gets released in seconds. This happens through rapid fault movement that can extend for hundreds of miles underground. During the 1964 Alaska earthquake, 500 miles of seafloor ruptured simultaneously. Some sections moved 60 feet horizontally and 30 feet vertically. This massive underground rebound generated seismic waves powerful enough to slosh water in swimming pools as far away as Texas. It also caused tsunamis that reached Japan 6 hours later. The elastic rebound process never truly ends along active fault systems. After major earthquakes release accumulated stress, tectonic forces immediately begin loading the fault zone again. This creates the next cycle of strain accumulation and release. This creates a geological rhythm where great earthquakes repeat at irregular but statistically predictable intervals. The southern San Andreas Fault gents magnitude 7 and above earthquakes roughly every 150 years. Earth's mantle functions like a planetary furnace where hot rock rises from near the core. It spreads horizontally beneath the crust, cools, and sinks back toward the depths. These massive circulation patterns have been running continuously for over 4 billion years. This underground hot water system, except with molten rock instead of water, provides the driving force behind all tectonic plate movement and surface geological activity. The energy source powering this geological circulation comes from radioactive decay within Earth's interior. Uranium, thorium, and potassium atoms constantly break apart and release heat. This equals 44 trillion watts of power. That's roughly 44,000 nuclear reactors running simultaneously underground. This enormous energy output keeps the mantle hot enough to flow like extremely thick honey. It circulates in convection currents that transport heat from Earth's core to the surface over millions of years. Hot mantle rock rises along narrow plumes. These can extend from 1,800 miles underground all the way to the surface. They create volcanic hotspots like Hawaii and Yellowstone. As this hot rock approaches the surface, it spreads horizontally beneath the tectonic plates. It gradually cools as it travels. Eventually, the cooled rock becomes dense enough to sink back toward Earth's core along subduction zones. This completes circulation cycles that last 200 to 500 million years. The scale of mantle circulation dwarfs any weather system operating at Earth's surface. Individual convection cells can span thousands of miles horizontally. They extend through the entire 1,800-mile thickness of the mantle. Material moving through these circulation patterns travels at speeds of 1 to 4 inches per year. That's roughly the same rate as plate movement at the surface. This isn't coincidence. Tectonic plates get dragged along by mantle circulation like leaves floating on very slow streams. Seismic waves from earthquakes reveal the three-dimensional structure of mantle circulation. They show how underground temperature variations affect wave speeds. Hot rock transmits seismic energy more slowly than cold rock. This allows geologists to map underground plumes and sinking slabs with remarkable precision. These seismic CT scans reveal mantle circulation as a complex network of rising and sinking currents. This connects volcanic activity, earthquake zones, and mountain building into a single unified system. Earth's interior dispatches a series of distinct messengers. Each carries different types of seismic information at different speeds toward the surface. The fastest messenger, called a primary wave or P wave, functions like an underground express delivery service. It always arrives first with urgent news. Major geological violence is approaching. Brace for impact. P waves earn their speed record by traveling through rock, using the most efficient possible motion. These waves compress and stretch underground materials in the same direction they're traveling. Think of pushing and pulling a giant spring that extends through solid earth. This compression technique allows P waves to maintain speeds up to 5 miles per second through dense rock. Through Earth's liquid outer core, they reach 8 miles per second. Here's what makes P wave motion so remarkably efficient. Unlike other seismic waves, P waves do not waste energy shaking rock side to side. They channel all their energy into straight-ahead compression pulses. These pulses squeeze through virtually any underground material. Rock, magma, water, even liquid metal. P waves push through everything. They behave like geological freight trains that refuse to be derailed by changes in material density. The compression motion creates a distinctive signature that seismologists can identify immediately. P waves produce the gentle up and down wiggles that appear first on seismograph records. Usually they're too subtle for humans to feel directly. People occasionally report hearing low rumbling sounds just before major earthquakes. That's often P wave compression traveling through rock and transferring into the air. But P waves' greatest talent lies in their role as earthquake early warning systems. Because they travel faster than more destructive seismic waves, P waves provide precious seconds of advance notice. Modern earthquake detection networks use P wave arrival times to automatically trigger emergency shutdowns. They stop nuclear reactors, halt high-speed trains, and send cell phone alerts to millions of people simultaneously. This underground express messenger service has become humanity's first line of defense against seismic surprise attacks. Secondary waves, or S waves, travel roughly 60% slower than their speedy predecessors. But they compensate for their leisurely pace by delivering devastating side-to-side motion. This motion topples buildings, cracks foundations, and turns solid ground into a chaotic carnival ride. No engineer ever designed structures to withstand this kind of violence. S waves generate their destructive power through shear motion. This moves rock perpendicular to the wave's direction of travel. Picture snapping a whip or shaking a rope. That wave-like motion racing along the length represents exactly how S waves propagate through underground rock formations. This side-to-side action hits structures at their weakest points. It creates the horizontal forces that cause most earthquake damage. The physics behind S-wave motion reveals why these underground messengers prove so much more dangerous. While P waves simply compress and release rock like a geological accordion, S waves twist and torque underground materials. They transfer maximum energy to anything sitting on the surface. This shearing action explains why moderate earthquakes can cause devastating structural damage, even when their overall energy release seems relatively modest on scientific scales. S-waves possess one remarkable limitation that proved crucial for understanding Earth's internal structure. These shear waves cannot travel through liquid materials at all. Geologists realized that S-waves from earthquakes on one side of the planet never appeared at detection stations on the opposite side. They discovered something important. Earth's outer core consists of molten metal. This liquid limitation creates fascinating patterns in how earthquake energy reaches different parts of the globe. Places directly opposite major earthquake sources experience only P waves. This creates relatively gentle shaking despite receiving energy from massive seismic events. Meanwhile, regions at intermediate distances get hammered by both P waves and S waves. This explains why earthquake damage doesn't always correlate directly with distance from the source. Modern building codes specifically target S-wave motion. These waves cause the structural failures that kill people and destroy property. Earthquake-resistant construction techniques focus on allowing buildings to flex and sway with S-wave motion. The goal is transforming structures into seismic dancers that can ride out the underground groove without breaking apart. Engineers essentially design buildings to dance with S-waves rather than fight them. Surface waves crawl along Earth's outer skin like geological tsunamis. They concentrate their energy in the uppermost layers where human civilization happens to reside. These waves move slower than both P waves and S waves, but they carry far more destructive energy and maintain their violence across much greater distances. Surface waves split into two distinct varieties that terrorize the landscape through different mechanisms. Love waves shake the ground horizontally in side-to-side motion similar to S waves, but with amplitude that can exceed 3 feet during great earthquakes. Rayleigh waves create rolling motion that moves both horizontally and vertically. They make the ground surface behave like ocean swells passing beneath ships. Both wave types can circle the entire globe multiple times before their energy finally dissipates. The concentration of surface wave energy in Earth's uppermost layers makes them particularly devastating. P waves and S waves spread their energy throughout Earth's interior volume. Surface waves channel almost all their power through the thin crustal layer. This is where cities, highways, and vital infrastructure happen to be located. This creates energy densities far exceeding what most structures can withstand. Surface waves cause the majority of earthquake damage despite arriving last at the scene. Surface wave motion defies everyday human experience with ground behavior. Eyewitness accounts from major earthquakes describe pavement rippling like water, manhole covers jumping 10 feet into the air, entire hillsides flowing downhill like thick liquid. During the 1964 Alaska earthquake, surface waves created visible ground rolls. These moved across the landscape like slow-motion tsunamis. They permanently altered the elevation of vast areas and created new lakes where none had existed before. The travel patterns of surface waves reveal why earthquake damage often appears mysteriously inconsistent. These waves follow complex paths that depend on underground geological structures. They amplify dramatically in some areas while bypassing others entirely. Soft sedimentary basins can trap and amplify surface wave energy like acoustic resonators. This creates localized zones of devastating shaking surrounded by areas that experience relatively mild motion. All from the same earthquake. When seismologists record the exact arrival times of P waves, S waves, and surface waves, they're collecting data for a sophisticated triangulation system. Monitoring stations around the world make it possible. This seismic timing network can pinpoint earthquake locations with remarkable accuracy. It uses nothing more than stopwatches and basic geometry. The mathematical elegance behind earthquake location calculations rivals any engineering achievement. P waves consistently arrive first, followed by S waves at predictable intervals. Then surface waves arrive at even longer delays. The time gaps between these arrivals reveal precise distances from earthquake sources. Seismic waves travel at known speeds through different underground materials. A 20-second delay between P-wave and S-wave arrivals indicates roughly 140 miles from the source. 3 widely separated monitoring stations can triangulate any earthquake's exact location using this travel time data. Each station provides distance information based on wave arrival intervals. This creates circles of possible earthquake locations. Where 3 circles intersect marks the precise spot where underground rock ruptured, usually accurate to within a few miles even for earthquakes occurring on the opposite side of the planet. This geological surveying technique works better than most GPS systems. The timing precision reaches levels that would impress atomic clock engineers. Modern seismographs can detect wave arrivals to within hundreds of seconds. This allows location calculations accurate to less than half a mile for nearby earthquakes. Global monitoring networks routinely determine earthquake locations within minutes of occurrence. They provide emergency responders with precise coordinates for search and rescue operations. This happens before news reports even confirm that earthquakes have occurred. But the real magic happens when seismologists reverse engineer earthquake properties from wave timing patterns. The duration of seismic wave arrivals reveals how long underground ruptures took to complete. This indicates fault zone dimensions. The relative amplitudes of different wave types reveal rupture direction. They also reveal the specific mechanisms behind underground rock failure. Wave frequency content indicates the depth where ruptures occurred and the types of rock materials involved. They provide detailed X-ray views of Earth's interior that no human technology could achieve through direct observation. When seismic waves from earthquakes travel through different underground materials, they bend, reflect, and change speed. These changes reveal the hidden architecture of our planet's interior. Geologists essentially perform CT scans on the entire Earth using earthquake energy as their imaging source. The breakthrough discovery came when seismologists realized that earthquake waves behave like light rays. They pass through lenses with different optical properties. Hot rock transmits seismic waves more slowly than cold rock. Liquid materials block S waves entirely while allowing P waves to pass through at reduced speeds. Dense materials speed up wave transmission while low-density zones create delays. These variations create detectable patterns that map underground temperature, density, and composition changes with remarkable precision. Seismic tomography uses thousands of earthquakes as illumination sources. It builds three-dimensional images of Earth's interior structure. Medical CT scans use multiple X-ray angles to image internal organs. Seismic tomography combines wave speed measurements from countless different earthquake sources. It uses detection stations to construct detailed pictures of underground geological features. The results reveal mantle plumes, subducting slabs, and thermal anomalies extending thousands of miles below the surface. This underground imaging reveals geological structures that completely revolutionized our understanding of Earth's interior operations. Seismic tomography discovered massive columns of hot rock rising from near Earth's core. These create volcanic hotspots like Hawaii and Iceland. It mapped cold, dense slabs of oceanic crust that have been sinking through the mantle. They've been falling for hundreds of millions of years after being subducted at ocean trenches. These structures show that Earth's interior maintains active circulation patterns extending from the surface all the way to the core. The resolution of seismic imaging continues improving as more earthquake data becomes available. Computer processing power advances. Modern seismic tomography can detect underground features as small as 50 miles across. This works at depths of 1,000 miles below the surface. This geological medical imaging reveals Earth's interior as a dynamic, three-dimensional structure. Hot and cold materials constantly circulate in patterns that control surface volcanic activity, earthquake locations, and mountain building processes. The earth trembled violently or buildings swayed like trees in a storm. These dramatic accounts told compelling stories, but provided no scientific framework. There was no way to compare different earthquakes or predict future seismic behavior. Everything changed in 1935. A brilliant seismologist named Charles Richter invented what would become geology's most famous measuring stick. It was a mathematical system that transforms chaotic ground motion into precise numerical ratings. Richter's scale operates on beautifully simple principles that any engineer would appreciate. Richter realized that earthquake strength could be quantified by measuring exactly how much seismograph needles wiggle. The bigger the wiggle, the stronger the earthquake. He established magnitude 0 as the threshold where sensitive seismographs just barely detect ground motion. Then he built a logarithmic scale. It could accommodate the enormous range between barely perceptible tremors and world-shaking catastrophes. Here's what makes Richter's system so elegantly practical. The scale measures earthquake energy at its source rather than damage at various locations. This provides objective ratings that work consistently anywhere on Earth. A magnitude 5.0 earthquake in Japan releases exactly the same underground energy as a magnitude 5.0 event in California, regardless of local soil conditions, building codes, or population density. The mathematical beauty behind Richter measurements lies in their logarithmic progression. Each whole number increase represents a 10-fold increase in seismograph needle amplitude. It also represents roughly a 32-fold increase in released energy. This exponential scaling lets one numerical system cover the vast energy range. It runs from micro-earthquakes that barely register on instruments to great earthquakes that release energy equivalent to thousands of nuclear weapons. Without logarithmic compression, earthquake scales would require impossibly large numbers. Richter's original scale worked perfectly for Southern California earthquakes recorded on specific types of seismographs. But it needed modifications to handle global earthquake monitoring using different instruments and detection methods. Modern seismologists have developed several refined magnitude scales. These preserve Richter's fundamental concept while extending accuracy across all earthquake sizes and recording conditions. The basic principle remains unchanged. Bigger needle wiggles mean stronger earthquakes. When earthquake magnitudes increase by one whole number, from 6.0 to 7.0 for example, the underground energy release does not simply double or triple. It multiplies by a factor of 32. This creates geological violence that escalates far faster than human intuition expects. This exponential fury scale explains why magnitude differences that seem small numerically correspond to catastrophic increases in destructive power. Picture trying to explain the difference between a hand grenade and a hydrogen bomb. You are using a scale where each number represents 32 times more explosive power than the previous number. That is essentially how earthquake magnitudes work. A magnitude 4.0 earthquake releases energy equivalent to about 1,000 tons of TNT, enough to rattle windows and wake sleeping people. A magnitude 5.0 event pumps out 32,000 of TNT equivalent. The exponential progression becomes truly staggering as magnitudes climb toward the upper end of the scale. A magnitude 7.0 earthquake releases roughly 32 million tons of TNT equivalent. That's about 2,000 times more energy than the atomic bomb dropped on Hiroshima. A magnitude 8.0 event multiplies that by 32 again. It reaches energy levels equivalent to over 1 billion tons of TNT. A magnitude 9.0 earthquake can release enough energy to power the entire United States for several months. This exponential scaling creates enormous practical consequences for earthquake preparedness and damage assessment. A city that successfully withstands a magnitude 6.5 earthquake might be completely devastated by a magnitude 7.5 event, despite the seemingly modest 1.0 difference in magnitude numbers. The 32-fold energy increase translates into ground motion intensities, structural loads, and secondary effects that overwhelm building codes. Understanding exponential progression becomes literally a matter of life and death for earthquake engineering. The mathematical reality behind earthquake magnitude progression reveals why great earthquakes remain relatively rare. Each magnitude level requires 32 times more energy than the previous level. Earth's underground stress systems can accumulate such enormous energy reserves only along the largest, most active fault zones. These operate over centuries or millennia. The exponential energy demands ensure that magnitude 9 and above earthquakes occur perhaps once per decade globally. Meanwhile, magnitude 6 and above events happen several times per month. This flaw became apparent when seismologists tried measuring the largest earthquakes on Earth. For truly massive seismic events, the magnitude 8 and above monsters that rupture hundreds of miles of underground rock, Richter measurements began saturating like overloaded electronic circuits. They provided inaccurate readings that underestimated the true scope of geological violence. Scientists needed an upgraded measurement system. It had to handle Earth's most extreme tantrums without breaking down. The breakthrough came with development of the moment magnitude scale. This measures earthquake size by calculating the total amount of rock displacement occurring during underground ruptures. Instead of relying solely on seismograph needle wiggles, this improved system considers the physical dimensions of fault ruptures. It considers the distance that rock moves along fault surfaces. It considers the strength of underground materials being fractured. This comprehensive approach provides accurate measurements for earthquakes across the entire possible size range. Moment magnitude calculations reveal earthquakes as massive underground construction projects. These reshape solid rock on scales that challenge human comprehension. The 2004 Indian Ocean earthquake ruptured 1,000 miles of seafloor. Sections of oceanic crust jumped 50 feet horizontally and 15 feet vertically in less than 10 minutes. The total rock displacement equaled moving a volume of stone larger than Mount Everest. The 2011 Japan earthquake shifted the main island 8 feet eastward. The improved measurement system also accounts for earthquake duration. Longer ruptures generally indicate larger fault zones and more extensive underground damage. Great earthquakes can continue rupturing for 3 to 5 minutes as underground fractures propagate along fault systems. These systems span multiple states or provinces. These extended rupture sequences release energy in complex patterns that cannot be captured by simple amplitude measurements. Modern seismologists use moment magnitude for all official earthquake size determinations. It provides consistent, accurate measurements regardless of earthquake size, recording distance, or instrument type. The scale preserves Richter's user-friendly numerical progression while extending measurement capability to handle the largest possible earthquakes. These are earthquakes that Earth's geological systems can generate. A magnitude 6.0 earthquake might cause devastating damage in one city. It might barely rattle dishes in another location. This depends on local soil conditions, building construction, and distance from the underground rupture. Scientists needed a separate rating system that measures earthquakes from the perspective of people actually experiencing the shaking. A geological customer satisfaction survey that asks, "How much did that earthquake ruin your day?" The modified Mercalli intensity scale provides exactly this human-centered earthquake rating system. It uses 12 levels of increasingly dramatic seismic experience. Intensity 1 describes earthquakes so gentle that only sensitive instruments detect them. Intensity 3 produces shaking noticeable to people at rest, similar to a large truck passing nearby. Intensity 6 causes everyone to feel the earthquake. Dishes break and people have trouble walking steadily. Intensity 9 destroys most masonry buildings and causes widespread panic among the population. The beauty of intensity measurements lies in their practical focus on earthquake consequences rather than abstract energy calculations. Intensity ratings describe exactly what people experience during earthquakes. Do hanging objects swing? Do people have difficulty standing? Do chimneys fall down? Does the ground crack visibly? This phenomenological approach creates earthquake descriptions that anyone can understand and apply. No advanced mathematics or seismological training required. Intensity measurements reveal fascinating patterns in how earthquake effects vary across affected regions. The same earthquake typically produces the highest intensities near the underground rupture source. Then it decreases with distance as seismic waves lose energy traveling through rock. But local geology creates dramatic exceptions to this pattern. Soft sedimentary soils amplify ground motion, sometimes producing higher intensities at great distances than occur in nearby areas with solid bedrock. The modified Mercalli scale also captures earthquake effect that magnitude measurements completely miss. Intensity ratings include secondary consequences like landslides, liquefaction, and ground ruptures. These often cause more damage than direct shaking. They document psychological impacts on affected populations. They describe damage patterns to different types of structures. This comprehensive approach creates earthquake portraits that combine physical measurements with human experience. A global network of ultra-sensitive earthquake detectors. It can monitor every significant tremor occurring anywhere on the planet. This geological intelligence network functions like a planetary stethoscope that never stops listening. It provides real-time data about seismic activity from the deepest ocean trenches to the highest mountain peaks. The modern global seismic network consists of over 3,000 monitoring stations. These are equipped with instruments sensitive enough to detect ground motion on the order of the width of an atom. These geological spy devices can sometimes register the footsteps of a single person walking 100 yards away. They detect the passage of ocean waves breaking on distant shores. They detect underground nuclear weapons tests conducted on the opposite side of the planet. The network operates with such precision that seismologists routinely detect earthquakes too small for anyone at the source location to feel. What makes this monitoring system truly extraordinary is its instantaneous global communication capability. When major earthquakes occur, seismic stations around the world detect the arriving waves within minutes. They automatically transmit their measurements to central processing centers via satellite links and internet connections. Computer algorithms analyze the incoming data streams to calculate earthquake locations, magnitudes, and other essential parameters. They do this faster than human operators could manually process the information. The global network provides early warning capabilities that transform earthquake disasters from surprise attacks into manageable emergency response scenarios. Automated systems can detect large earthquakes and issue warnings to affected populations within seconds of underground rupture initiation. This provides precious time for protective actions before the most destructive seismic waves arrive. Modern earthquake alert systems have helped prevent casualties by automatically stopping elevators, shutting off gas lines, and sending emergency notifications to millions of smartphones. This planetary monitoring network also enables scientific discoveries that would be impossible using isolated regional systems. By combining seismic data from stations worldwide, researchers can track how earthquake waves travel through Earth's entire interior. This reveals details about underground structure, composition, and dynamics. The global network functions like a geological CT scanner that uses earthquake energy to create three-dimensional images of our planet's hidden interior. Perhaps most remarkably, the global seismic monitoring system operates as an unintentional nuclear weapons verification network. A fracture zone so enormous and active it has shaped the entire state's landscape, economy, and earthquake anxiety for over 150 years. The San Andreas Fault stretches 800 miles from the Mexican border to Cape Mendocino. It marks the boundary where two massive pieces of Earth's crust grind past each other in slow-motion geological violence. This makes California the most seismically active region in the continental United States. This underground monster represents far more than a simple crack in the ground. The San Andreas Fault system consists of a complex network of parallel and intersecting fractures. These extend up to 10 miles deep and 20 miles wide in some locations. The main fault trace alone has accumulated over 350 miles of total displacement during its 15 to 20 million year history. Rocks that started their journey side by side now sit hundreds of miles apart on opposite sides of the fracture zone. What makes the San Andreas truly extraordinary is its relentless persistence in moving California toward Alaska. The Pacific Plate, carrying Los Angeles and everything west of the fault, slides northwest at roughly 2 inches per year. This rate is relative to the North American plate. This doesn't sound particularly threatening until you realize that 2 inches per year accumulates to 16 feet per century. San Francisco and Los Angeles gradually creep toward each other along this geological conveyor belt. The fault's movement pattern creates a complex puzzle of earthquake hazards that varies dramatically along its length. Some sections slide smoothly through gradual creep that relieves stress without generating major earthquakes. Other segments remain locked together by friction. They accumulate stress for decades or centuries before releasing it catastrophically in great earthquakes. These can be felt across multiple states. The southern San Andreas hasn't generated a major earthquake since 1857. This creates a 160-year stress accumulation period that seismologists find deeply concerning. Modern research reveals the San Andreas as a geological time bomb with multiple triggers that could activate simultaneously. The fault connects to dozens of secondary fractures throughout California. This creates a network where ruptures on one segment can trigger failures across the entire system. California exists in a state of permanent geological alert. It would terrify residents if they truly understood the seismic violence beneath their daily routines. The Golden State experiences over 10,000 earthquakes annually. That's roughly 30 earthquakes every single day. This makes it the most seismically hyperactive region in North America. This is an occasional geological drama, but constant underground conversation. Fault systems never stop adjusting stress, releasing pressure, and preparing for their next major performance. Los Angeles sits atop a nightmare scenario of intersecting fault systems. These create earthquake hazards from virtually every direction. The city sprawls across a complex web of active fractures. These include the San Andreas, San Jacinto, Puente Hills, and dozens of smaller faults. These can generate damaging earthquakes independently or in devastating sequence. The 1994 Northridge earthquake demonstrated how even moderate events on relatively unknown faults can cause billions of dollars in damage. San Francisco faces equally daunting seismic challenges from its position directly atop multiple major fault systems. The San Andreas Fault passes just 6 miles west of downtown San Francisco. Meanwhile, the Hayward Fault runs directly beneath the heavily populated East Bay communities of Oakland and Berkeley. The 1989 Loma Prieta earthquake provided a terrifying preview of the region's vulnerability. A magnitude 6.9 event 60 miles south of the city caused the Bay Bridge to collapse. It killed 63 people throughout the metropolitan area. What makes California's earthquake situation uniquely dangerous is the concentration of population and critical infrastructure in areas of highest seismic risk. Over 38 million people live within California's earthquake zones. Major metropolitan areas are built directly on or adjacent to active fault systems. The state's economy, transportation networks, and emergency response capabilities all depend on infrastructure that must function during and immediately after major seismic events. These events occur with statistical certainty over timescales measured in decades rather than centuries. California's geological hyperactivity stems from its position at the intersection of multiple tectonic plate boundaries. These create overlapping earthquake hazards throughout the state. The San Andreas system dominates the landscape, but hundreds of smaller faults contribute to the constant seismic background noise. Seismologists have identified over 300 potentially active faults throughout the state. This creates a geological minefield where major earthquakes can strike almost anywhere with little advance warning. The Yellowstone caldera represents one of Earth's most powerful volcanic systems. It's capable of explosions so massive they would make typical earthquakes seem like minor inconveniences. This underground monster has erupted catastrophically 3 times during the past 2.1 million years. It created volcanic winters that altered global climate and covered half of North America in volcanic ash several feet deep. The earthquake activity at Yellowstone provides a geological early warning system for one of the most potentially destructive forces on the North American continent. The region experiences over 1,500 earthquakes annually as underground magma chambers expand, contract, and shift. These respond to the massive heat engine operating several miles beneath the surface. Most of these tremors remain too small for tourists to feel. But they create patterns that scientists monitor obsessively for signs that the supervolcano might be stirring toward another catastrophic awakening. What makes Yellowstone earthquakes uniquely ominous is their connection to a volcanic system that dwarfs conventional geological hazards. The underground magma chamber extends roughly 30 miles long, 20 miles wide, and 5 miles deep. This represents a molten rock reservoir larger than the entire city of Los Angeles. When this system eventually erupts again, The resulting explosion will release energy equivalent to thousands of nuclear weapons. It will inject enough ash into the atmosphere to block sunlight across the entire northern hemisphere for months or years. The earthquake swarms that periodically shake Yellowstone create both scientific fascination and existential dread among geologists who understand the implications. In 1985, a magnitude 6.1 earthquake near the northwest corner of the park demonstrated how seismic activity can trigger massive landslides. It altered the behavior of geothermal features throughout the region. More concerning, major earthquakes in volcanic regions sometimes precede eruptive activity. They trigger changes in underground magma behavior that can destabilize volcanic systems. Modern monitoring reveals Yellowstone as a restless giant where earthquake patterns, ground deformation, and gas emissions fluctuate constantly. The underground volcanic system breathes like a sleeping dragon. The caldera floor rises and falls by several inches annually as magma chambers expand and contract with temperature changes. Earthquake swarms occur every few years as underground stresses adjust to ongoing geological processes. Scientists emphasize that Yellowstone shows no immediate signs of approaching eruption, but the earthquake activity provides constant reminders that North America's most dangerous geological feature remains very much alive. In the heart of America's agricultural heartland, most people assume earthquakes simply don't happen. But one of the continent's most puzzling and potentially dangerous seismic zones lies there. The New Madrid area of southeastern Missouri gained instant notoriety during the winter of 1811 to 1812. It generated the most powerful sequence of earthquakes in recorded American history. Seismic violence so extreme it temporarily reversed the flow of the Mississippi River and rang church bells in Boston over 1,000 miles away. The New Madrid earthquakes challenged everything geologists thought they understood about where major seismic events could occur. This region sits in the middle of the North American plate. It lies hundreds of miles from any active plate boundaries where earthquakes typically concentrate. Yet during a 3-month period, the area produced at least 3 magnitude 7 or higher earthquakes. It also generated over 2,000 smaller tremors that were felt across an area 10 times larger than California earthquake zones typically affect. Eyewitness accounts from the 1811 to 1812 sequence describe geological violence that defies modern comprehension. The ground rolled in visible waves like ocean swells. Entire forests were submerged as the landscape sank by 15 feet across vast areas. New lakes formed overnight, including Tennessee's Reelfoot Lake, which still exists today. The Mississippi River temporarily flowed backward as seismic waves created upstream surges that overwhelmed the normal current direction. What makes the New Madrid seismic zone particularly unsettling is its location in a region completely unprepared for major earthquake damage. The 1811 to 1812 earthquakes occurred when the area was sparsely populated frontier territory. Today, the same region contains major cities like Memphis and St. Louis. It contains extensive industrial infrastructure and millions of people living in structures never designed to withstand seismic forces. A repeat of the 1811 to 1812 earthquake sequence would affect 44 states and cause catastrophic damage across the entire central United States. Modern research reveals New Madrid as a geological mystery where ancient weaknesses in the continental crust continue generating earthquakes. These happen through mechanisms that remain poorly understood. The seismic zone appears to follow buried fault systems created when North America nearly split apart 550 million years ago. These left permanent scars in the bedrock that occasionally reactivate under modern stress conditions. The region continues producing magnitude 3 to 4 earthquakes several times per year. This maintains a level of seismic activity that suggests the underlying geological problems haven't been resolved. This northern frontier sits directly on the Pacific Ring of Fire. Oceanic crust plunges beneath the North American continent in a massive subduction zone that generates the largest earthquakes possible on Earth. Alaska doesn't mess around with moderate seismic events. It specializes in magnitude 8 or higher monsters that release energy equivalent to hundreds of nuclear weapons. These can be detected by sensitive instruments anywhere on the planet. The 1964 Good Friday, Alaska earthquake established the gold standard for seismic violence in North America with a magnitude 9.2 rating. This makes it the second largest earthquake ever recorded worldwide. This geological beast ruptured over 500 miles of underground fault surface. It lifted entire coastlines by 30 feet. It dropped other areas below sea level. It triggered tsunamis that killed people as far away as Oregon and California. The earthquake released roughly 250 times more energy than the 1906 San Francisco event. Alaska's earthquake potential stems from its position, where the massive Pacific Plate continuously dives beneath North America. This happens at rates of 2 to 3 inches per year. This creates a geological conveyor belt where oceanic crust gets forced into the deep underground. It generates enormous stress that accumulates for centuries before releasing catastrophically in great earthquakes. The Aleutian Trench marking this subduction zone extends 2,500 miles from the Alaska Peninsula to the Kamchatka Peninsula in Russia. This creates the longest active earthquake zone in the world. What makes Alaskan earthquakes uniquely terrifying is their ability to generate devastating tsunamis that threaten coastlines throughout the Pacific Ocean. The 1964 earthquake produced waves up to 200 feet high along some Alaskan shores. It sent tsunamis racing across the Pacific at jet aircraft speeds. These seismic sea waves caused deaths and damage in California, Oregon, Washington, Hawaii, and Japan. This demonstrates how Alaskan earthquakes create hazards that extend thousands of miles beyond their underground sources. Modern seismologists identify Alaska as capable of producing the largest earthquakes physically possible on Earth. The state experiences magnitude 7 or higher earthquakes roughly every year. It sees magnitude 8 or higher events every decade. This maintains a level of seismic hyperactivity that would terrify residents of any more densely populated region. Fortunately, the state's sparse population and earthquake-resistant indigenous building traditions minimize casualties. But Alaska serves as a constant reminder. Earth's geological machinery operates on scales that dwarf human civilization's ability to control or fully defend against seismic catastrophes. A geological domino effect that transforms underground rock ruptures into massive waves capable of crossing entire ocean basins at jet aircraft speeds. Tsunamis represent earthquake energy's most far-reaching consequence. They carry seismic violence thousands of miles from its underground source to devastate coastlines that never felt the original earthquake. These aren't ordinary waves enlarged by seismic activity, but entirely different oceanic phenomena. They behave more like liquid avalanches racing across the sea surface. The tsunami generation process begins with underwater earthquake ruptures that suddenly displace enormous volumes of seafloor. When magnitude 8 or higher earthquakes occur beneath the ocean, they can lift or drop sections of sea bottom spanning hundreds of square miles. This happens by 10 to 50 feet in less than 2 minutes. This instantaneous reshaping of underwater terrain forces massive amounts of seawater upward or downward. It creates the initial energy pulse that eventually becomes tsunami waves racing toward distant shores. What makes tsunamis so uniquely destructive is their ability to maintain enormous energy levels across vast distances. Unlike wind-driven ocean waves that affect only surface waters, tsunami waves involve the entire water column from surface to seafloor. Sometimes this extends 15,000 feet deep. This gives them incredible momentum and staying power as they race across ocean basins at speeds approaching 500 miles an hour in deep water, fast enough to cross the entire Pacific Ocean in less than 24 hours. The physics behind tsunami wave behavior creates one of nature's most deceptive weapons. In deep ocean waters, tsunami waves remain nearly invisible. They rise only 1 to 3 feet above normal sea level and pass beneath ships without being noticed. But as these hidden monsters approach shallow coastal waters, they undergo a dramatic transformation. This concentrates their enormous energy into towering walls of water that can exceed 100 feet in height along some shorelines. The 2004 Indian Ocean tsunami demonstrated the global reach of earthquake-generated waves. A magnitude 9.1 earthquake off Indonesia created waves that killed over 230,000 people in 14 countries. The tsunami traveled 3,000 miles across the Indian Ocean to devastate coastlines in Thailand, Sri Lanka, India, and East Africa. Waves arrived up to 7 hours after the original earthquake. This catastrophe revealed tsunamis as earthquake consequences that can affect more people and cause more damage than the underground ruptures that create them. Liquefaction occurs when earthquake shaking causes water-saturated sandy soils to lose their structural integrity and behave temporarily like liquid materials. This underground sleight of hand can cause buildings to sink, tilt, or topple over even during moderate earthquakes. It creates damage patterns that seem to defy logic and engineering expectations. The liquefaction process operates through principles that would fascinate any materials scientist. Loose sandy soils normally maintain their strength through friction between individual sand grains. They also rely on water pressure in tiny spaces between particles. During earthquake shaking, vibrations cause sand grains to pack more tightly together. This squeezes water upward through the soil like a geological sponge being compressed. As water pressure increases, it eventually overcomes the friction holding sand grains together, causing the entire soil mass to behave like a dense liquid. What makes liquefaction particularly insidious is its tendency to occur in areas where people assume the ground provides the most stable foundation. Coastal areas, river deltas, and filled marshlands often contain exactly the type of loose, water-saturated sandy soils that liquefy most readily during earthquakes. These locations typically support high population densities and extensive infrastructure. They offer flat terrain, water access, and rich agricultural potential. These advantages disappear instantly when the ground transforms into liquid. The visual effects of liquefaction create some of earthquake geology's most spectacular and terrifying phenomena. Sand volcanoes erupt through pavement as pressurized water carries sand grains to the surface in muddy geysers. Manholes pop out of the ground like champagne corks. Entire buildings sink several feet into liquefied soil while remaining structurally intact. This creates neighborhoods where houses sit at crazy angles like a geological fun house. Cars and trucks become partially buried in what was solid pavement just minutes earlier. The 1964 Alaska earthquake provided classic examples of liquefaction's power to reshape landscapes and destroy infrastructure through ground failure rather than direct shaking damage. The Turnagain Heights neighborhood in Anchorage experienced catastrophic liquefaction that caused entire city blocks to slide toward the ocean. This carried away 75 homes and created a moonscape of broken ground and tilted structures. Similar liquefaction failures during the 1989 Loma Prieta earthquake caused billions of dollars in damage to San Francisco's Marina District, where buildings constructed on liquefaction-prone filled land suffered disproportionate damage compared to structures on more stable soils. Massive slope failures occur minutes, hours, or even days after the original seismic shaking ends. These gravity-powered chain reactions transform earthquake energy into avalanches of rock, soil, and debris that can travel for miles from unstable slopes. They create destruction patterns that extend far beyond areas that experienced direct earthquake damage. The relationship between earthquakes and landslides operates through a deadly combination of reduced slope stability and gravitational forces. These forces never stop trying to pull hillsides downward. Earthquake shaking temporarily weakens the bonds holding slope materials together while simultaneously providing the trigger motion that overcomes friction and initiates catastrophic failure. Steep slopes that remained stable for centuries can suddenly collapse during earthquake shaking, releasing enormous volumes of rock and soil that bury valleys, block rivers, and destroy anything in their path. What makes earthquake-triggered landslides particularly dangerous is their ability to affect areas that experience relatively minor seismic shaking. A moderate earthquake occurring in mountainous terrain can destabilize hundreds of slopes simultaneously. This creates a delayed destruction scenario where landslides continue occurring for weeks after the original earthquake. These secondary failures often prove more deadly than direct earthquake damage. They strike without warning in areas where people assume the seismic danger has passed. The scale of earthquake landslide activity challenges human comprehension of how much Earth's surface can change in a matter of minutes. The 2008 Wenchuan earthquake in China triggered over 200,000 landslides across a region spanning 44,000 square miles. This fundamentally altered the landscape of entire mountain ranges. Some individual landslides involved over 100 million cubic yards of rock and bris. That's enough material to bury Manhattan under 30 feet of rubble. Earthquake landslides also generate their own secondary hazards that can affect areas hundreds of miles downstream from the original slope failures. When massive landslides block river valleys, they create temporary lakes that eventually overtop or breach the natural dams. This sends catastrophic floods racing downstream with little advance warning. The 1959 Hebgen earthquake in Montana triggered a landslide that created a 200-foot-high natural dam. It formed a new lake that threatened downstream communities until engineers could construct emergency spillways. It breaks through to ground level in spectacular displays of geological force that slice through roads, pipelines, buildings, and anything else unfortunate enough to sit directly above active fault zones. Surface fault ruptures represent earthquake destruction at its most direct and unstoppable. They create linear zones of devastation where the underground fracturing process literally cuts through human civilization. This happens like a geological lightsaber emerging from Earth's interior. Surface ruptures occur when underground fault movement extends all the way from deep source regions to Earth's surface. This creates visible breaks in the ground that can extend for hundreds of miles. The 1906 San Andreas earthquake generated surface ruptures stretching 250 miles from San Francisco to Southern California. Some sections displayed horizontal offsets exceeding 20 feet. Fences, roads, and streams that crossed the fault zone were suddenly displaced by distances that horses and carriages couldn't cross. This created barriers that isolated entire communities for weeks after the earthquake. What makes surface fault ruptures uniquely terrifying is their ability to destroy infrastructure through direct, cutting action rather than simple shaking damage. No amount of earthquake-resistant construction can protect a building that sits directly on top of a fault line when the underground fracture extends to the surface. The geological forces involved can slice through reinforced concrete, steel frameworks, and bedrock with equal ease. They create destruction patterns that look like giant invisible knives cutting through the landscape. The mechanics behind surface rupturing reveal the enormous energies involved in major earthquake generation. When underground stress finally overcomes rock's strength along fault zones, the resulting fracture can propagate upward through miles of solid rock at speeds approaching 2 miles per second. This underground zipper effect eventually reaches the surface, where it continues racing along the ground at speeds that outrun most vehicles. Eyewitness accounts describe surface ruptures opening like geological lightning bolts that appear and disappear faster than human reaction times can follow. Surface fault ruptures create permanent geological monuments to earthquake violence that remain visible for centuries after the seismic events that created them. The fault scarps generated by major earthquakes become permanent features in the landscape. They record the accumulation of thousands of individual rupture events over millions of years. These geological staircases reveal fault zones as ancient pathways of weakness where Earth's crust repeatedly fails under stress. Linear zones where surface rupturing will inevitably occur again during future major earthquakes. Spring locations and aquifer behavior change across vast regions. These hydrological chain reactions occur as seismic waves compress and fracture underground rock formations. They open new pathways for water movement while sealing others. The result is geological plumbing chaos that can dry up wells, create new springs, and transform the underground water infrastructure that supports entire ecosystems and human communities. The mechanics behind earthquake-induced groundwater changes involve complex interactions between seismic waves and the underground fracture networks that control water movement through rock formations. When earthquake waves pass through water-bearing rock layers, they create compression and expansion cycles. These can permanently alter the permeability of underground materials. Previously sealed fractures can be forced open, creating new channels for groundwater flow. Existing water pathways can be compressed shut, redirecting underground streams into entirely different routes. What makes earthquake hydrology particularly fascinating is its ability to affect areas hundreds of miles from earthquake sources through subtle changes in underground pressure systems. Even moderate earthquakes can trigger changes in groundwater levels, spring flow rates, and artesian well behavior across regions that experienced no direct seismic damage. The 1935 Long Beach earthquake in California caused water level changes in wells throughout the southwestern United States. This demonstrated how seismic waves can conduct long-distance underground hydraulic surgery. The temperature effects of earthquake-altered groundwater systems create some of geology's most spectacular secondary phenomena. When earthquakes open new fracture pathways that connect surface aquifers with deep geothermal systems, cold springs can suddenly begin producing hot water. Deeper, heated groundwater finds new routes to the surface. Conversely, disruption of existing geothermal circulation patterns can cause hot springs to cool dramatically or stop flowing entirely. Their underground heat sources get redirected through different fracture networks. Historical examples reveal earthquake groundwater changes as powerful forces that can reshape regional hydrology for decades or centuries. The 1811 to 1812 New Madrid earthquakes altered groundwater systems throughout the central Mississippi Valley. They caused some wells to run dry while creating new springs in previously arid areas. Eyewitness accounts describe water gushing from the earth in areas that had never shown signs of underground water. Formerly reliable springs disappeared permanently after the earthquake sequence. Modern monitoring of earthquake groundwater effects reveals these hydrological changes as sensitive indicators of underground stress conditions. They can provide early warning of seismic activity. Changes in groundwater chemistry, temperature, and flow rates often precede major earthquakes by days or weeks. This suggests that underground water systems respond to stress accumulation before rocks actually rupture. However, the same sensitivity that makes groundwater useful for earthquake prediction also ensures that major seismic events will continue conducting unpredictable underground plumbing renovations. Swarms of earthquakes reveal magma's violent journey toward Earth's surface. These volcanic earthquakes represent some of geology's most dramatic opening acts. Molten rock forces its way upward through solid stone barriers with explosive determination. Unlike the tectonic earthquakes that dominate most seismic activity, volcanic earthquakes tell stories of underground fire fighting its way toward daylight. They push through rock formations that never intended to let it pass. Volcanic earthquake generation operates through mechanisms that would fascinate any demolition expert. As underground magma chambers expand with fresh molten rock from deeper sources, they create enormous pressure. This pressure fractures surrounding rock formations in characteristic patterns. The magma doesn't politely find existing pathways to the surface. It creates new routes by hydraulically fracturing solid rock through pure thermal violence. Each crack represents a small earthquake, and active volcanic systems can generate thousands of these fracturing events. What makes volcanic earthquakes uniquely recognizable is their distinct signature that differs dramatically from normal tectonic seismic activity. Volcanic earthquakes typically occur in tight clusters directly beneath volcanic systems at depths ranging from surface level to 10 miles underground. They follow ascending patterns as magma intrusions work their way toward the surface. This creates earthquake sequences that literally map the underground pathways of rising molten rock. Seismologists can track magma movement in real time by monitoring these earthquake patterns, essentially watching underground volcanic plumbing systems activate through seismic surveillance. The frequency and intensity of volcanic earthquakes provide crucial early warning signs of impending eruptions that can save thousands of lives. Mount Steed. Helens generated over 10,000 small earthquakes during the 2 months preceding its catastrophic 1980 eruption. This created a seismic drumroll that announced the volcano's awakening with unmistakable clarity. These earthquake swarms intensified dramatically during the final weeks before eruption. Magma approached the surface and began interacting directly with groundwater systems. Each type of geological violence can trigger the other in escalating feedback loops that amplify destruction beyond what either phenomenon could achieve independently. This underground collaboration operates like a geological casino where volcanic explosions and seismic shaking continuously raise the stakes. They trigger each other in unpredictable chain reactions that can devastate entire regions through combined fire and shake destruction. Key: the mechanisms behind volcano-earthquake interactions involve complex stress transfer processes that connect these seemingly separate geological phenomena. Large earthquakes can destabilize magma chambers by altering underground pressure conditions. This triggers volcanic eruptions that might otherwise remain dormant for decades or centuries. Conversely, major volcanic eruptions can trigger earthquake swarms by rapidly changing subsurface stress distributions. Magma chambers empty and surrounding rock formations readjust to fill the void. Historical examples reveal volcano-earthquake partnerships as particularly lethal combinations that create destruction patterns exceeding simple addition of volcanic and seismic hazards. The 1815 eruption of Mount Tambora in Indonesia triggered massive earthquake sequences that continued for months after the initial volcanic explosion. This created a prolonged disaster scenario where survivors of the eruption faced ongoing seismic violence. Similarly, large earthquakes in volcanic regions often precede eruptive activity by days or weeks. This suggests that seismic shaking can serve as the final trigger that pushes marginally stable volcanic systems over the threshold into explosive activity. What makes volcano-earthquake interactions particularly unpredictable is their tendency to occur in cascading sequences. Initial events trigger multiple secondary disasters across extended time periods. The 1783 Laki eruption in Iceland generated both massive volcanic emissions and prolonged earthquake sequences that affected European climate and agriculture for several years. The volcanic gases altered atmospheric conditions while ongoing seismic activity prevented effective disaster response and recovery efforts. This created compound disasters that exceeded the impact of either phenomenon alone. Modern monitoring reveals volcano-earthquake interactions as active processes occurring in volcanic regions worldwide. Seismic networks detect systematic relationships between earthquake patterns and volcanic activity. The 1980 Mount Seats Helen's eruption sequence demonstrated how earthquakes can directly trigger catastrophic volcanic explosions. Seismic shaking destabilizes volcanic slopes and triggers massive landslides that suddenly decompress magma chambers. This particular interaction mechanism creates some of the most explosive volcanic events possible, where seismic triggers amplify volcanic violence far beyond normal eruption scales. These supervolcanic systems, marked by massive calderas that can span 30 to 50 miles across, maintain underground magma chambers larger than entire metropolitan areas. The earthquake activity generated by these sleeping giants operates on scales that dwarf normal volcanic seismicity. It creates persistent tremor patterns that reveal ongoing activity in underground chambers capable of explosive power that could alter global climate. Caldera earthquake systems operate through mechanisms that demonstrate the enormous scales involved in supervolcanic activity. The magma chambers beneath calderas like Yellowstone and Long Valley contain hundreds of cubic miles of molten or partially molten rock. These are maintained at temperatures exceeding 1,500 degrees Fahrenheit. These vast underground furnaces generate constant thermal expansion and contraction cycles that fracture surrounding rock formations. They create earthquake patterns that reflect the breathing of geological dragons large enough to swallow entire mountain ranges. What makes caldera earthquakes uniquely ominous is their connection to volcanic systems capable of catastrophic global impacts. The Yellowstone supervolcano has erupted 3 times during the past 2.1 million years. It created volcanic winters that affected worldwide climate and covered half of North America in volcanic ash several feet deep. The earthquake swarms that currently shake Yellowstone with over 1,500 tremors annually provide constant reminders. This geological weapon of mass destruction remains very much alive and periodically restless. The earthquake patterns generated by supervolcanic systems reveal complex underground processes that operate on timescales spanning thousands of years. Caldera floors rise and fall by several inches annually as underground magma chambers expand in contract with temperature fluctuations and gas content changes. These vertical movements create characteristic earthquake signatures that allow scientists to monitor the health and activity level of supervolcanic systems. They use seismic surveillance networks that never stop listening for signs of awakening giants. Long Valley Caldera in California demonstrates how supervolcanic earthquake activity can escalate into crisis situations that threaten regional populations. During the 1980s, the caldera experienced dramatic earthquake swarms accompanied by ground uplift of nearly 2 feet. Underground magma intrusions altered stress conditions throughout the volcanic system. This activity prompted emergency preparedness measures and evacuation planning. It prepared for scenarios where one of North America's largest volcanic systems might transition from dormant giant to active supervolcano. Modern monitoring of caldera earthquake systems reveals these supervolcanic features as restless geological time bombs. Seismic activity provides the only advance warning of potential eruptions that could affect entire continents. A real-time volcanic symphony where underground magma movement creates continuous earthquake concerts that have been playing without intermission for decades. These volcanic earthquake swarms represent active geological processes happening in real time. Every tremor tells a story about magma flowing through underground conduits like molten blood circulation through a planetary cardiovascular system that never stops pumping. Kilauea's earthquake orchestra operates through mechanisms that provide unprecedented insight into how active volcanic systems function on daily and hourly timescales. As magma moves through underground tube systems toward active lava flows, it generates distinctive earthquake signatures. These reveal the location, direction, and intensity of underground molten rock transport. Scientists can literally listen to the volcano's pulse through seismic monitoring networks. They detect every underground magma heartbeat with remarkable precision. The earthquake patterns generated by Hawaiian volcanism demonstrate how volcanic systems maintain continuous underground activity even during periods of relatively quiet surface eruption. Kilauea produces thousands of small earthquakes annually as magma circulates through complex underground plumbing networks. These extend from deep source regions to active surface vents. This persistent seismic activity reveals volcanoes as dynamic systems that never truly rest. Even when they appear dormant from surface observation. What makes Hawaiian volcanic earthquake swarms uniquely valuable for science is their accessibility and safety for detailed study. Unlike explosive volcanic systems that threaten researchers with deadly eruptions, Hawaiian shield volcanoes allow scientists to deploy sensitive monitoring equipment directly on active volcanic slopes. This is where earthquake swarms occur. This proximity enables real-time correlation between underground earthquake patterns and surface volcanic activity. It creates detailed understanding of volcano-earthquake relationships that would be impossible to obtain from more dangerous volcanic systems. The frequency and character of Kilauea's earthquake swarms change dramatically during different phases of volcanic activity. This creates seismic signatures that forecast eruption behavior with remarkable accuracy. Increased earthquake activity typically precedes new eruption episodes by days or weeks as magma moves from deep storage areas toward surface vents. Changes in earthquake depth patterns reveal whether magma is rising toward new eruption sites or draining from existing active areas. This provides advance warning of volcanic behavior changes that affect both scientific research and public safety. Modern volcanic earthquake monitoring at Kilauea has revolutionized understanding of how active volcanic systems operate through continuous underground processes that generate persistent seismic activity. The volcano's earthquake swarms function like geological telegraph systems that broadcast real-time information about underground magma behavior. Scientists have learned to interpret these seismic messages as reports from an underground correspondent covering volcanic activity from inside the action. This ongoing earthquake symphony ensures that Hawaiian volcanoes serve as natural laboratories where volcano-earthquake relationships can be studied in unprecedented detail. Supercontinents assemble and disintegrate in cycles spanning hundreds of millions of years. The seismic violence we experience today represents just the latest scene in an ongoing geological epic. This epic has been reshaping our planet's surface since solid rock first formed from the primordial magma ocean. Each geological era featured dramatically different earthquake patterns as continents danced across the globe in configurations that would astound any modern geographer. During the Archean and Proterozoic eons, spanning Earth's first 4 billion years, earthquake activity operated under completely different rules than today's plate tectonics. The early Earth was so hot that crustal rocks behaved more like thick putty than brittle materials capable of sudden fracture. Instead of sharp earthquake ruptures, early geological violence expressed itself through slow ductile deformation and massive volcanic activity. This gradually assembled the first stable continental masses. The Paleozoic era witnessed some of the most spectacular tectonic violence in Earth's history. All existing continents gradually assembled into the supercontinent Pangaea between 550 and 250 million years ago. This continental merger generated earthquake zones that dwarfed anything in the modern world. It created mountain ranges like the Appalachians through collision events that lasted tens of millions of years. The seismic energy released during Pangaea's assembly exceeded the total earthquake energy of the past million years. All of it concentrated into collision zones where entire ocean basins disappeared as continents crushed together. Pangaea's breakup during the Mesozoic era created the earthquake patterns that still dominate global seismicity today, beginning about 200 million years ago. This supercontinent began rifting apart along massive fracture systems. These eventually became the Atlantic and Indian Ocean basins. The initial rifting process generated earthquake swarms that persisted for millions of years as continental crusts stretched and failed along zones. These zones are now marked by passive continental margins thousands of miles from active earthquake zones. The Cenozoic era, spanning the past 65 million years, established modern earthquake geography through the ongoing breakup of ancient continental connections. It also developed current plate boundary configurations. The formation of the Himalayan mountain range through India's collision with Asia created earthquake zones that continue generating magnitude 8 or higher events today. The opening of the Red Sea and East African rift systems initiated new earthquake zones. These may eventually split Africa into separate continents. Paleoseismology, the science of reading earthquake history from geological records, has uncovered evidence of prehistoric mega-earthquakes. These generated ground motion and destruction patterns far exceeding anything in recorded human experience. These geological detective stories reveal Earth's seismic past through subtle clues preserved in sedimentary layers, fault exposures, and landslide deposits. These serve as stone libraries documenting millions of years of earthquake activity. The techniques used to decode ancient earthquake evidence would impress any forensic investigator. Geologists excavate trenches across fault zones to expose layered sediments that record individual earthquake ruptures. These appear as offset boundaries between different age deposits. Each earthquake leaves a distinctive signature in the geological record. Broken layers, tilted strata, liquefaction features, and debris flows can be precisely dated using radiocarbon analysis and other geochronological methods. These earthquake fingerprints allow scientists to reconstruct detailed histories of seismic activity extending back thousands of years before written records began. Some of the most spectacular paleoseismic discoveries reveal prehistoric earthquakes that generated landscape changes visible from space even today. The Bonneville landslide in the Columbia River Gorge resulted from a magnitude 9 or higher Cascade subduction zone earthquake about 500 years ago. This triggered a debris avalanche large enough to temporarily dam the Columbia River. Similar paleoseismic evidence throughout the Pacific Northwest reveals a history of magnitude 9 or higher earthquakes occurring every 300 to 600 years. The most recent event in 1700 generated tsunamis that reached Japan and were recorded in historical documents there. Paleoseismic research in California has uncovered evidence of prehistoric San Andreas Fault earthquakes. These exceeded the famous 1906 San Francisco event in both magnitude and destruction patterns. Offset stream channels displaced geological markers, and sedimentary records reveal ancient earthquakes that ruptured over 600 miles of the fault system simultaneously. These generated ground motion that would dwarf modern building code requirements. These paleoseismic discoveries forced complete revision of California earthquake hazard assessments and building code requirements. They account for prehistoric events that generated violence levels previously considered impossible. The global paleoseismic record reveals ancient earthquake activity that challenges modern assumptions about maximum possible earthquake sizes and recurrence intervals. Evidence from the Himalayas suggests prehistoric earthquakes with magnitudes approaching 9.5. These ruptured fault zones extending over 1,000 miles. Paleoseismic studies in the eastern United States have uncovered evidence of ancient earthquakes in regions now considered seismically quiet. This reveals that earthquake activity migrates over geological time as stress patterns and crustal weaknesses evolve. This accidental earthquake manufacturing represents one of the most dramatic examples of human impact on natural geological processes. Activities designed to extract resources or store waste have fundamentally altered regional earthquake patterns across vast areas of North America and other continents. The scale of human-induced earthquake activity has reached levels that rival natural seismic processes in some regions. Oklahoma experienced a 2,500% increase in earthquake activity between 2009 and 2015. This transformed it from one of America's quietest seismic regions into one of its most active through injection well operations. These dispose of billions of gallons of wastewater underground annually. This dramatic earthquake acceleration demonstrates how human activities operating on industrial timescales can alter geological processes. These processes normally require centuries or millennia to modify natural stress patterns. Hydraulic fracturing operations have created entirely new categories of earthquake hazards through underground pressure injection techniques. These deliberately fracture rock formations to extract oil and natural gas. These intentional rock-breaking activities generate thousands of micro-earthquakes as part of their normal operation. But they also occasionally trigger larger seismic events when fracturing operations intersect pre-existing fault systems. The largest fracking-induced earthquake on record reached magnitude 5.7 in Oklahoma. It shows that human earthquake manufacturing can produce seismic events capable of significant structural damage. Underground mining operations have generated some of the most dramatic examples of human earthquake triggering through excavation activities. These alter stress distributions across vast underground areas. Coal mining in regions like Utah and West Virginia regularly produces magnitude 4 or higher earthquakes. These occur as underground chambers collapse or when mining operations intersect natural fault systems. These mining-induced earthquakes often occur in populated areas where buildings were never designed to withstand seismic forces. This creates unique hazard scenarios where industrial activities generate earthquake risks in previously safe regions. The reservoir-induced seismicity phenomenon reveals how even water storage can trigger significant earthquake activity when large dams create artificial lakes. These alter underground stress conditions. The filling of Lake Mead behind Hoover Dam triggered hundreds of earthquakes as the enormous weight of impounded water stressed underlying rock formations in new ways. Similar reservoir-induced earthquake sequences have occurred worldwide, with some reaching magnitudes exceeding 6.0. They caused significant damage to the dams and infrastructure they were designed to protect. Scientists can predict how Earth's earthquake geography will evolve as continents continue their slow-motion dance across the globe. These long-term tectonic forecasts reveal a future world where current earthquake zones will become geologically quiet. New seismic violence will emerge in regions that now seem permanently stable. The predictability of plate motion ensures future earthquake patterns follow the same fundamental rules. Earthquake zones will still migrate across the planet's surface. The most dramatic changes in future earthquake geography will result from ongoing continental drift that gradually repositions major landmasses. The Atlantic Ocean continues widening by 2 inches annually. This means that in 200 million years the distance between North America and Europe will increase by over 600 miles. This expansion will eventually position the current east earthquake zones far from active plate boundaries. It will transform regions like the New Madrid seismic zone from active earthquake areas into geologically quiet continental interiors. Meanwhile, the Pacific Ocean shrinks as oceanic crust gets consumed in subduction zones around the Ring of Fire. This fundamentally alters earthquake patterns throughout the Pacific Basin. California's ongoing northward drift along the San Andreas Fault system will eventually carry Los Angeles past San Francisco and toward the Alaska-Russia connection. This creates entirely new earthquake zones as the western United States slides into different tectonic figurations. These predictable motions ensure that future California earthquake geography will bear little resemblance to current seismic hazard patterns. The formation of future supercontinents represents the most spectacular long-term earthquake forecast. Computer models predict that current continental positions will eventually lead to new continental collision zones. These will generate earthquake activity dwarfing anything in modern experience. Several competing models suggest different assembly patterns for future supercontinents. But all scenarios involve massive continental collisions that will create mountain ranges and earthquake zones far larger than current examples. These include examples like the Himalayas or the Andes. Climate change may also influence future earthquake patterns through mechanisms that connect surface processes with deep geological activities. The melting of massive ice sheets alters surface loading patterns. This can affect underground stress distributions and may modify earthquake timing along existing fault systems. Rising sea levels will change coastal loading patterns, while shifting precipitation patterns may alter groundwater systems. These influence earthquake processes in subtle but potentially significant ways. Perhaps most remarkably, future earthquake geography will eventually eliminate many current seismic hazards while creating entirely new ones. Plate motions continue reshaping Earth's surface according to the same physical laws that have operated for billions of years. The earthquake zones that currently threaten millions of people represent temporary features in the ongoing geological transformation. This will continue long after human civilization has either adapted to or been replaced by whatever species inherits Earth's dynamic surface. These geological fortune-telling exercises show how current seismic violence fits into much larger patterns of planetary change. Those patterns operate on timescales spanning hundreds of millions of years.